Summary. According to the collision theory, effective collisions result in reaction. There are two criteria for reaction to occur. When colliding, reactant particles must be correctly oriented and have enough kinetic energy Ke greater than or equal to Ea, where Ea is activation energy, which is the minimum amount of energy needed to start a reaction. An activated complex is also known as a transition state, which is a transient species that forms during an effective collision when reactants just begin to form new bonds and break old bonds. The higher the temperature, the greater the number of particles with kinetic energy that is greater than or equal to activation energy to undergo reaction. The rate of a reaction is directly proportional to the number of collisions per second. Experimental methods to find rate of reaction may be carried out by measuring change in amount of reactant or product by titration, pressure in a closed reaction vessel for gases, color intensity of reaction mixture, and conductivity of ions. Rate of reaction is the change in reactant concentration or product concentration over time. There are different ways to express rate of reaction, which is a positive quantity. Instantaneous rate is the rate at a particular moment in time. It is found via the slope or gradient of the tangent of the reactant concentration against time graph. Average reaction rate. There are two ways to express this. A decrease in reactant concentration per unit time. Rate of reaction is equal to the negative of change of reactant concentration over change in time, which is equal to the negative of final reactant concentration minus initial reactant concentration divided by final time minus initial time. Since final reactant concentration is less than initial reactant concentration, final reactant concentration minus initial reactant concentration divided by final time minus initial time is less than zero. For rate to be positive, this fraction has to be multiplied by minus. Increase in product concentration per unit time. The rate of reaction is equal to change in product concentration over change in time, which is equal to final product concentration minus initial product concentration divided by final time minus initial time. Reaction rate from a balanced or stoichiometric equation. For example, if R moles of reactant R gives P moles of product P, then the rate of reaction is the negative of the reciprocal of the reactant's stoichiometric coefficient times change in reactant concentration over change in time, which is also equal to the reciprocal of the product's stoichiometric coefficient times the change in product concentration over change in time. The rate law is also known as the rate equation. It relates the reaction rate with rate constant and reactant concentrations. It is experimentally determined and not obtained from the balanced or stoichiometric equation. It may or may not include all or any of the reactants. The general form of the rate law is rate of reaction is equal to K times concentration of A raised to power X times concentration of B raised to power Y, where K is the rate constant. K is unchanged as reaction proceeds at a particular temperature. The units of K depend on the overall order of reaction. X is the order of reaction with respect to A concentration, Y is the order of reaction with respect to B concentration, and X plus Y is the overall order of reaction. Order of reaction with respect to reactant. It is expressed in terms of reactant, not product. It is the power or exponent of the reactant concentration in the rate equation. It tells us how much rate is affected by changes in reactant concentration. Experimental methods to determine reaction rate. The initial rate method. Use the rate law, which is rate is equal to rate constant K times concentration of A raised to power X times concentration of B raised to power Y, concentration and initial rate data to calculate order of reaction, initial rate, rate law, rate constant, and rate of reaction. Graphical method. Find order of reaction and rate constants from the following graphs. When the order of reaction of a reactant is zero, its concentration against time graph is a straight line with negative gradient or slope, since the reactant is consumed over time. For the slope to be negative, we draw the graph starting from the top left of the vertical axis, which is the concentration of reactant axis. Then we end the straight line graph at the bottom right of the horizontal axis, which is the time axis. The rate is minus times the negative gradient of the graph to ensure that rate is a positive quantity. For a zero-order reactant, its rate against reactant concentration graph is a horizontal straight line since the rate does not vary when the reactant concentration changes. When the order of reaction of a reactant is 1, its concentration against time graph is a curve with negative gradient or slope since the reactant is consumed over time. The gradient starts off relatively steep, then becomes less steep over time. For a first-order reactant, its rate against reactant concentration graph is a straight line with a positive gradient. When the order of reaction of a reactant is 2, its concentration against time graph is a curve with negative gradient or slope since the reactant is consumed over time. The gradient starts off steeper than the corresponding graph for a first-order reactant, then becomes less steep over time. For a second-order reactant, its rate against reactant concentration graph is a curve with a positive gradient. An increase in reactant concentration brings about a more rapid increase in the rate. Factors affecting rate of reaction. Chemical nature of reactants. The fewer and weaker the bonds, the faster they break, the faster the reaction. Concentration. Increasing reactant concentration increases collision chances, which increases number of effective collisions and increases reaction rate. Surface area of solid. Increasing surface area of solid reactant increases reaction rate. Temperature. Often, increasing temperature causes more reactants to have kinetic energy that is greater than or equal to activation energy, resulting in effective collisions and increased reaction rate. Catalyst. There are two types, heterogeneous and homogeneous. A catalyst provides an alternative pathway with lower activation energy to increase reaction rate. More reactants have kinetic energy greater than or equal to activation energy, resulting in effective collisions and increased reaction rate. It does not increase yield. It does not change energies of reactants and products. Though it takes part in reaction, it is regenerated after reaction. Increasing the surface area of a solid catalyst increases reaction rate. Watch the TED-Ed video on chemical kinetics. Click on the link shown.